Okay, welcome back to the deep dive. Today, we're really getting into the weeds on something pretty critical in web security. We're tackling you could say, the unholy trinity of web application forgery attacks.
Right, we're talking cross-site scripting, or XSS, cross-site request forgery, CSRF, and server-side request forgery, SSRF. They sound similar, maybe, but they're fundamentally different beasts.
Exactly. And you, our listeners, asked us to dig into a whole pile of research on this, and what really jumps out is, well, these aren't some brand new zero-day type things, are they?
Not at all. They've been around, documented since the early 2000s, really.
Yeah.
But they are still showing up constantly, top of the OWASP, top 10 lists, year after year.
It's kind of wild that they're so persistent. So the core idea we need to unpack is how they mess with trust, right? Each one targets a different trust relationship on the web.
That's the perfect way to frame it. Seriously, if you get that, you're halfway there. Because the defenses depend entirely on which trust relationship is being broken.
Okay, so let's break that down. XSS, that's about the user trust in the website.
Exactly. XSS breaks the trust you have that the content shown by a website is safe. The attacker injects malicious code right into the page you're looking at.
Okay. Then CSRF. That flicks it.
Right. CSRF exploits the trust the website has in your browser. It assumes requests coming from your browser with your session cookie are actually things you intended to do.
Ah, okay. The confused deputy problem, I think I've heard it called.
That's the one. And then SSRF, that's the server trusting itself or its own network.
Yeah, SSRF is where it gets really insidious, maybe. The attacker tricks the server into making requests on its behalf, often into the internal network, leveraging the server's own trusted position.
So yeah, 3 different trust models, 3 different attack vectors. Our goal today really is to get into the nuts and bolts of how each one works, look at how attackers actually use them. We'll touch on the MITRE ATT and CK framework there, and then most importantly, talk about building layered defenses, moving past just, one single fix.
Towards what you called perfect injection resistance. Sounds ambitious.
Well, it's a mindset, right? Striving for it. It means understanding these nuances deeply because, like I said, the mitigations are fundamentally different for each one. Confuse XSS with CSRF, and your defense won't work.
Got it. Okay, let's start with the first one then. XSS, the client-side compromise. All right, XSS. You said it's about injecting malicious script, usually JavaScript, into a trusted web page, and then someone else views it.
That's the core loop. Attacker injects, victim views, script runs, and the absolute key is where that script runs.
In the victim's browser, right?
Yes, but crucially, it runs in the context of the vulnerable website. It's not running from evil.com. It's running as if it's part of your-bank.com.
Ah, okay. And that's what gets it past the browser's main security guard, the same origin policy.
Precisely. The SOP is designed to keep evil.com's scripts from grabbing data from your-bank.com. But because the XSS script is running effectively from your-bank.com, the SOP doesn't apply between the script and the site it's running on.
So the script basically inherits all the permissions and trust associated with that site.
Exactly. It can read cookies associated with that domain.
Session cookies, the important ones.
Absolutely. Session tokens, authentication cookies. It can also access data stored in local storage or session storage for that domain. It can potentially scrape the entire page content, modify what the user sees.
Like changing bank balances shown on the screen, or inserting fake login forms.
You got it. Or adding keyloggers to capture credentials as they're typed. It can make requests back to the attacker server, sending stolen data. It's incredibly versatile once that code execution is achieved.
So credential theft is probably the most common goal.
It's definitely up there. Session hijacking via stolen cookies is classic, but don't underestimate the others. Data manipulation, defacement, making a site look bad, or spreading misinformation, and advanced phishing.
How does that work? Like, more than just a fake login?
Yeah, imagine the script waits until you interact with a real form on the site, maybe the actual login form. It grabs your credentials before they're submitted, sends them off to the attacker, and then lets the real login proceed. Or maybe redirects you somewhere else entirely, like a malware download page. It's much harder to spot than a standard phishing email link.
Okay, that's nasty. So how does this malicious script actually get onto the page? You mentioned there are different ways, and that affects how we find it.
Right, 3 main flavors here. First, and often considered the most dangerous, is stored XSS or persistent XSS.
Stored, meaning it's saved somewhere on the server.
Exactly. The attacker injects the payload maybe into a comment field, a user profile, a forum post, product review, Anything that gets saved in the application's database and then displayed later to other users.
So the attacker injects it once.
And it just sits there. Every single user who views that specific comment or profile or whatever gets hit by the payload automatically. No extra steps needed.
That sounds really bad. Maximum impact for minimum ongoing effort from the attacker.
Totally. That's why it's seen as so potent. The example from the sources, the Elementor page builder vulnerability, that was a stored XSS issue. Think about how many websites use a popular page builder. A single flaw there could mean widespread compromise.
Okay, so that's stored XSS. What's the second type?
That's reflected XSS, or non-persistent. Here, the payload isn't stored on the server permanently.
Right, it's reflected, meaning...
Meaning the payload is part of the request itself, usually embedded in a URL parameter. Think of a search results page. Maybe search.php.queryscript.alert, XSS script. If the server takes that query parameter and just dumps it straight back into the HTML response without cleaning it.
The script gets reflected back to the user who made the request.
Exactly. The server echoes it back, the browser renders the page, sees the script tag, and runs it.
But wait, if the user has to put the script in their own request, how does that help the attacker?
The user doesn't type it in themselves. The attacker has to trick the user into submitting that request.
Social engineering time?
Bingo. Phishing emails with crafted links, malicious posts on forums, maybe compromising another site to create a watering hole that redirects users with the payload. The attacker needs to get the victim to click the link while they are logged into the target site.
So it requires that extra step of trickery for each victim.
It does, which makes it maybe slightly less dangerous overall than stored, but still very effective. The JetBrains TeamCity vulnerability mentioned was a case of reflected XSS.
Okay, stored and reflected. Both involved the server handling the script somehow. What's the third one?
The third one is DOM-based XSS, and this one is a bit mind-bending sometimes because it can happen entirely on the client side without the payload ever touching the server.
Whoa. How does that work?
It happens when client-side JavaScript, legitimate JavaScript already on the page, takes data from an untrusted source.
Like the URL.
Exactly, often the URL. And it writes that data directly into the page's structure, the document object model, or DOM, in an unsafe way. This writing location is called a sink.
So JavaScript reads from a source, writes to a sink, and if the data isn't cleaned, boom.
Pretty much. For example, maybe some JavaScript reads the page title from a URL parameter, title myPageScript, and writes it directly into an h1 tag using inner HTML. If the input isn't sanitized first, the script gets written into the DOM and executed.
And you mentioned something about the URL fragment making this extra sneaky.
Yes. This is crucial for detection. Often the payload for DOM-based XSS is put in the URL after the hash symbol, hashtag, the fragment identifier.
Like page.html user-data-script.script.
Exactly. And the key thing is, web browsers do not send the fragment part of the URL to the server in the HTTP request.
Seriously, the server never sees it.
Never sees it. So think about your defenses. Web application firewalls, server-side input validation, server logs. They all work by inspecting the HTTP request if the payload isn't in the request.
They're completely blind to it.
Utterly blind. Detecting DOM-based XSS requires analyzing the client-side JavaScript code itself, looking for those unsafe source-to-sink flows. It's a different kind of analysis.
Okay, that makes sense. So 3 vectors. Stored, reflected, DOM-based. Let's map this back to how attackers operate using MITRE ATT and CK. You said XSS is often about getting that first foot in the door.
Absolutely. Within the ATT and CK framework, XSS falls squarely under the initial access tactic, which is TA0001. The specific technique is TLEMA 189, drive-by compromise.
Drive-by. Like the user just visits a page and gets compromised.
That's the idea. The adversary injects their malicious script into a legitimate site, maybe via stored XSS, or tricks the user into visiting a site where the script runs automatically, reflected or DOM-based, and that's enough to gain some level of access or execute code in the user's context.
And this isn't just script kiddie stuff. Serious actors use this.
Oh, absolutely. The sources mentioned APT28, also known as Fancy Bear, a well-known state-sponsored group. They used reflected XSS vulnerabilities in government websites.
To do what? Steal data directly?
In that case, their goal was redirection. They used the XSS to bounce authenticated users from the legitimate government site to sophisticated phishing pages designed to steal credentials for other government systems. It shows how XSS can be a stepping stone in a much larger campaign. It's not always the end goal. Sometimes it's just the entry point.
Right, enabling the next stage of the attack. Okay, so if we know the types and how attackers use it, how do we defend? You said perfect injection resistance involves layers. Validate input feels insufficient.
It is insufficient on its own. Though it's the crucial first step, input validation and sanitization has to be rigorous. Don't just check if input looks okay, define exactly what is okay. Strict length checks, character set restrictions, data type enforcement. Whitelisting allowed patterns is always better than blacklisting bad ones.
But what about things like comment fields where users need some formatting, like bold or italics? You can't just strip all HTML.
Exactly. That's where generic validation breaks down. For any kind of rich text input where you need to allow some HTML, you absolutely must use a dedicated, battle-tested HTML sanitization library. Things like OWASP Anti-SAMI or DOM Purify for client-side sanitization.
How do those work differently?
They don't just look for bad tags. They actually parse the incoming HTML, build an internal representation of it, and then reconstruct the output using only a strict whitelist of allowed tags, like BIP, and allowed attributes, like href but not onClick. Anything not explicitly allowed is simply discarded. It rebuilds safe HTML from the ground up.
Okay, so clean the input aggressively. What's the next layer? You mentioned encoding.
Yes, output encoding and escaping. This is arguably even more critical, your safety net. The idea is when you take data, even data you think is safe, maybe you came from your database, and you put it back into an HTML page to display to a user, you must encode appropriately for the specific context where it's being placed.
Encode it, like turn special characters into harmless versions.
Exactly. The most common is HTML entity encoding. If a user managed to sneak script into their username, when you display that username, you don't output script, you output NLT, script ngd.
Ah, so the browser sees an alt and just displays the literal character vet. It doesn't interpret it as the start of a tag.
Precisely. It treats the whole thing as plain text to be displayed, not code to be executed. And the key is context. Encoding for HTML content is different from encoding needed inside an HTML attribute like href, which is different again from encoding needed inside JavaScript code or inside CSS. You need the right encoding for the right place.
That sounds complicated. Do modern web frameworks help with this? I hear people say things like, oh, React protects me from XSS.
They help a lot, but it's a dangerous assumption to think they make you immune. Most modern frameworks like React, Angular, Vue use templating systems that automatically perform context-aware output encoding by default. You just put a variable in your template like named div, it will likely be safely encoded.
So where's the danger?
The danger comes when developers bypass the framework's safety mechanisms. Maybe they need to render HTML dynamically, using functions like dangerously setinner HTML in React, or they construct HTML strings manually, or they put user data into unsafe places like JavaScript event handlers, onClick, without proper encoding for that specific context. The framework protects the common cases, but developers need to understand where those protections end and what to do then.
Okay, so framework defaults are good, but know the edge cases. Is there another layer we can add, like at the browser level?
Yes, Content Security Policy, CSP. This is a powerful defense mechanism implemented via an HTTP response header sent from the server.
How does CSP work?
It basically tells the browser, here's a list of rules about where content on this page is allowed to come from. You can define policies like scripts can only be loaded from my own domain, self, and from apis.google.com, or even stricter, no inline scripts allowed at all.
So if an attacker manages to inject, say, script src http.evil.com forgeries.badlib.js,
and your CSP says scripts can only come from self, the browser will simply refuse to load or execute the script from evil.com. It blocks the attack even if the injection and encoding defenses failed.
Wow, okay, so CSP is like a final gatekeeper at the browser.
It's a very effective layer, especially against classic reflected and stored XSS. It can also help mitigate some forms of data exfiltration. Implementing a strict CSP is highly recommended.
Right, defense in depth, validate sanitize input, encode output correctly for context, use safe frameworks wisely, and implement CSP.
That's the multi-layered approach you need.
Let's quickly revisit those case studies to see the real-world impact. The MySpace Sammy worm back in 2005, that was legendary, right?
Oh yeah, classic. Sammy Kamkar found a clever way to bypass MySpace's HTML sanitization for profile fields. His payload was ingenious because it wasn't just malicious, it was viral.
How did it spread so fast?
The JavaScript payload did two things. First, it added Sammy as a friend to the victim's profile.
Right.
Second, and this is the killer part, it copied itself the entire malicious script onto the victim's own profile page.
So anyone visiting that profile page got infected and spread it further.
Exactly. Exponential growth. It infected over 1 million profiles in something like 20 hours. It perfectly demonstrated the devastating potential of stored XSS when combined with a self-replicating payload.
A very different kind of attack was the British Airways breach in 2018. That wasn't directly attacking BA's site.
No, that was a supply chain attack, facilitated by XSS. The attackers, part of the Magecart group, compromised a third-party JavaScript library, a chat and analytics tool called Feedify that British Airways used on its payment pages.
So they injected malicious code into that script.
Yes, they modified the Feedify script to include card skimming code. When a customer entered their credit card details on the BA payment page, the compromised script silently grabbed the details and sent them off to the attacker's server before the data even reached BA's systems.
Wow. So BA's own servers could have been secure, but the third-party script betrayed them.
Precisely. It hit around 380,000 transactions. A huge lesson about the risks of embedding third-party scripts, especially on sensitive pages. You inherit their vulnerabilities.
And lastly, the eBay vulnerabilities between 2015 and 2017, that was reflected XSS used for fraud.
Yeah, that was a clear case of reflected XSS leading to direct financial impact. Attackers found they could inject script via an unvalidated URL parameter used for some kind of redirection or framing on the site.
So they'd craft a malicious eBay link.
Right. Send it to a seller, perhaps. If the seller clicked it while logged in, the injected script executed in their browser context, giving the attacker control over their session.
What could they do with that control?
They could manipulate the seller's listings, change prices, descriptions, maybe redirect payments for high-value items like cars. It allowed them to commit ongoing fraud by hijacking legitimate seller accounts. It highlights how even seemingly harmless parameters, if not handled safely, can be attack vectors.
Okay, so XSS is clearly a major threat. Let's move on to the next one. CSRF. All right, shifting gears to CSRF. You said XSS attacks the user's trust in the site's content, but CSRF attacks the site's trust in the user's browser. It's about stolen intent, not stolen code execution in the browser.
That's a great way to put it. Cross-site request forgery doesn't involve injecting script into the target site. Instead, it exploits how browsers handle sessions automatically.
Meaning the automatic sending of cookies.
Exactly. When you log into a website, say your-bank.com, the site sets a session cookie in your browser.
Yeah.
From then on, for every single request your browser makes to your-bank.com, it automatically includes that cookie.
Right. That's how the site knows it's still you.
Yes, but the browser does this regardless of where the request originated from. It could be from you clicking links on the bank site itself, or it could be triggered by a resource loading on a completely different website, like evil-cat-pictures.com.
Wait, so if evil-cat-pictures.com includes like an image tag whose SRC points to an action on your-bank.com?
Your browser will dutifully make that request to your-bank.com, and it will automatically attach your-bank.com session cookie to that request.
Even though the request came from a totally unrelated site.
Yep. The bank server receives the request. It sees a valid session cookie. As far as the server is concerned, the request is authenticated and legitimate. It has no idea you didn't intend for that request to happen.
So the browser is the confused deputy. It has the authority, the cookie, but it's being told what to do by the wrong party, the attacker site.
Exactly. The attacker isn't stealing your password or your cookie directly. They are leveraging your existing authenticated session to make the browser send unintended commands on your behalf.
Okay, let's use that e-commerce example to make it concrete. How would an attacker force me to buy something?
Okay, imagine you're logged into examplebuy.com. The attacker does some reconnaissance and finds out the purchases are made via a simple GTAT request, maybe something like https://shop-purchase.producted123 in amount 10.
Using GET for a purchase already sounds like a bad idea.
It's a terrible idea, precisely because of CSRF. But let's run with it. The attacker wants you to buy, say, product ID 999 for $500, maybe ship to their address if they can control that too, so they craft that URL, https://shop-purchase.producted999 in amount 500.
Okay, they have the malicious URL, now what?
They need to get your browser to send it. The classic trick is to embed it in an MMG on a different website, maybe one they control, or in an email they send you, like magsrc https://examplebuy.com /shop-purchase.producted999 in amount 500 with height 0.
A 0-pixel image, so I won't see it.
Exactly. You visit the attacker's page or open the malicious email while you're still logged into examplebuy.com. Your browser sees the MMG tag, tries to load the image from that URL,
Automatically attaches the examplebuy.com cookie.
sends a request. Examplebuy.com receives it, sees the valid cookie, thinks a user wants to buy product 999 for $500, and processes the order. You might not even realize anything happened.
Yikes. Okay, so using GET for actions that change state is rule number 1 of what not to do.
Absolutely fundamental. Any action that changes data, creates, updates, deletes something, must use a method like post, pushy, or delete. It shouldn't be possible via Guillaume.
Can CSRF still work against post requests?
Yes, it's just slightly trickier for the attacker. They can't use a simple MG tag. Instead, they typically create a hidden HTML form on their malicious page.
A form that mimics the real form on the target site.
Exactly. It would have the correct action URL pointing to the target site's endpoint, method, post, and hidden input fields containing the malicious data, like the product ID, amount, maybe the attacker's shipping address.
And how do they submit it without me clicking a button?
Usually with a tiny bit of JavaScript on their page that automatically submits the hidden form as soon as you load the page. Document.form0.submit. Same result. Your browser sends the POC request, automatically includes the cookies, and the server gets tricked.
Okay, so Piece2 helps, but doesn't solve it entirely.
Yeah.
Where does CSRF fit in the IRE, ATT, and CK lifecycle? It's not initial access like XSS often is.
Right. CSRF is typically a post-authentication technique. It assumes the victim is already logged in. It often falls under tactics like execution or impact. You can map it to techniques like T1134, access token manipulation using the existing session token, or T1530, data manipulation, forcing actions like transfers or purchases. It's about doing something with the access you already have, or rather, the access the victim has.
That ING direct bank vulnerability from 2008 sounds like a textbook example of relying just on cookies.
It was a shocking oversight for a bank. Reports at the time indicated you could potentially craft a simple request, maybe even a GT request initially, to transfer funds between accounts, and the only check was the presence of a valid session cookie. No check to ensure the request actually originated from the bank's own web interface.
Wow. So how do we actually prevent this? If cookies are automatically sent, how does the server know if the request was intended?
The gold standard defense is using anti-CSRF tokens.
Okay, what are those and how do they work?
The basic idea, known as the synchronizer token pattern, works like this. 1. When the user logs in, the server generates a unique, secret, unpredictable token associated with that user's session. 2. When the server sends a page containing a sensitive form, like transfer funds or change password, it embeds this secret token as a hidden field within the form. 3. When the user submits the form, the browser sends the data and the hidden token back to the server. 4. Crucially, the server validates that the token received in the form submission matches the token it stored for that user's session.
Ah, I see. The attacker on their evil-cat-pictures.com site has no way of knowing what that secret token is for my current session on your-bank.com, right?
Exactly. The same origin policy prevents the attacker's site from reading content, like the hidden token, from the bank site. So when the attacker forces your browser to submit the forged request via the hidden image or auto-submitting form, that request will be missing the valid token or have an incorrect one.
And the server just rejects it.
Rejects it flat out. Token doesn't match. Request is invalid. CSRF attempt blocked.
That sounds pretty robust. You mentioned different patterns like double submit cookie. How's that different?
Right. The double submit cookie pattern is often used in stateless architectures, where keeping session state on the server is tricky, like with microservices or certain API setups.
Okay.
Here, when the user visits a page with a form, the server still generates a unique token. But instead of storing it server-side, it sends it to the client in 2 places, once as a regular cookie and again as a hidden field in the form, or maybe an HTTP header.
So the token is sent twice.
Yes. When the user submits the form, the browser sends back the form data, including the token from the hidden field, and it automatically sends the token that was stored in the cookie. The server's only job, then, is to check if the token value from the form field matches the token value from the cookie.
How does that stop the attacker? They could forge the hidden field, couldn't they?
They could forge the hidden field, yes, but they cannot read or set the cookie for the target domain, your-bank.com, from their malicious site, evil-cat-pictures.com, because of the same origin policy. So they can't make the cookie value match the forged form value.
Ah, so the server just needs to check, do these 2 values, one from the form, one from the cookie, match? If yes, it's likely legitimate. If no, it's likely CSRF.
Exactly. It achieves the goal without requiring the server to maintain session state for the tokens.
Clever. Okay, so anti-CSRF tokens are key. What else? There's something about cookies themselves having a new attribute. Same site.
Yes, the same-site cookie attribute is a huge step forward, implemented at the browser level. It provides another strong layer of defense, sometimes even sufficient on its own, depending on the setting.
How does it work?
You can set the same-site attribute on your cookies to one of three values: strict, lax, or none. Same-site strict is the most secure. If a cookie has this attribute, the browser will only send it in requests originating from the exact same site that set the cookie. It will not send it with any cross-site requests, not even when you click a regular link from another site to get there.
So strict basically breaks CSRF completely because the cookie just isn't sent with the forged request.
Pretty much, yes. It's very effective. The downside is it can sometimes break legitimate cross-site workflows, like clicking a link from an email to go directly to a logged-in page.
Ah, okay, so what's lax?
Same-site lax is the default in many modern browsers now. It's a compromise. It does prevent the cookie from being sent on cross-site sub-requests, like loading images, iframes, or using XHR fetch, which blocks most common CSRF methods, including the PUSD via hidden form trick.
Ooh.
But it does allow the cookie to be sent when a user navigates cross-site via a top-level GET request, like clicking a normal link. So if your application still has critical actions vulnerable via GET, which it shouldn't, lax might not fully protect you.
And none just means it's sent with everything, like the old days.
Right. Same-site none, which also requires the secure attribute, meaning HTTPS only, is needed for things like cross-site tracking cookies or embedded content that needs session state. But for your main session cookie, you definitely don't want none.
So the recommendation is use strict if you can, lax as a good default, and always combine with anti-CSRF tokens for belt and suspenders protection.
That's the best practice, absolutely. Relying solely on same-site lax might leave gaps.
Okay, makes sense. We already covered don't use get-tay for state changes. Is there anything else on the server side?
One more check you can sometimes do is origin referer header validation.
Checking where the request came from.
Yeah. Browsers typically include an origin header for post, put, delete, etc., or a referer header for get and others, though less reliable, indicating the domain the request originated from. For sensitive actions, your server can check if these headers match your own domain or a list of trusted domains. If they're missing or point to evil-cat-pictures.com, you could reject the request.
Is that reliable? Can attackers spoof those headers?
Attackers generally can't spoof them directly in a standard CSRF scenario because the request is made by the victim's browser, which sets them correctly. However, the headers might sometimes be missing, example, due to privacy settings or transitions from HTTPS to HTTP, so relying only on this check isn't foolproof. It's best used as an additional defense layer alongside tokens and same-site cookies.
Got it. Tokens, same site, no GT for state changes, and maybe origin referer checks. That seems like a solid defense against CSRF.
It is. When implemented correctly, CSRF should be a solvable problem.
Okay, on to the third member of the Trinity, SSRF. All right, SSRF, server-side request forgery. You said this one's different because the server becomes the attacker's tool, targeting its own internal network. This sounds particularly bad.
It really is. SSRF flips the script entirely. Instead of attacking the user's browser, like XSS, or the user session, like CSRF, the attacker finds a vulnerability that lets them force the web application server itself to make arbitrary HTTP requests to destinations chosen by the attacker.
So the attacker says, hey, web server, go fetch this URL for me.
Basically, yes. Often the vulnerability lies in functionality, where the server needs to fetch a resource based on user input. Maybe it imports data from a URL, fetches a user's profile picture from a link they provide, calls a webhook, or queries an internal API based on some parameter, if the application doesn't strictly validate what URL it's being asked to fetch.
The attacker can point it anywhere, like inside the company's private network.
Exactly. That's the core danger. The attacker provides a URL pointing to an internal IP address, like 10.0.5 or 192.168.1 over 0.1 or even the server's own loopback address, 127.0.0.1.
And why is that so bad? Why can't the attacker just scan those IPs directly from the outside?
Because those internal IPs are usually protected by firewalls. They're not reachable from the public internet. But the web server, it sits inside that protected network perimeter, or at least has access to parts of it.
Ah, so the request originates from the web server's trusted internal IP address.
Precisely. As far as the internal database server or the admin tool at 10.0.0.5 is concerned, the request is coming from a friendly neighbor, the web server. It bypasses perimeter firewalls completely.
Okay, the implications are starting to sink in. What kind of damage can an attacker do once they have this SSRF capability?
The impact is often severe and leads to deeper compromise. A major risk, especially in cloud environments, is sensitive data exposure.
How so?
Cloud platforms like AWS, Azure, and GCP provide an internal metadata service accessible via a special non-routable IP address, like 169.254.169.254 in AWS. This service provides information about the running server instance, including
Yeah.
temporary security credentials like IAM role keys.
Wait, so the attacker can use SSRF to make the web server query its own metadata service and steal its credentials?
Yes. If the server instance has an associated IAM role, which is common practice, the attacker can forge a request to http:169.254.169.254 latest metadata and security credentials role name, and the server might just hand over powerful temporary keys. This was the core mechanism in the Capital One breach.
That's horrifying. Okay, what else besides stealing cloud keys?
Internal network scanning and reconnaissance. Even if the SSRF doesn't return the content of the internal resources, maybe it's a blind SSRF, the attacker can use it like a port scanner. They make the server request http://0.0.0.0.0.0.0.0.0.0.0.0.0.0.2.80, and so on.
How does that help if they don't see the response?
They can analyze the response time or error messages from the vulnerable web server. A quick connection refused error means the port is closed. A connection timeout might mean the IP exists, but the port is firewalled or filtered. A successful connection, even if no data comes back, or a specific error message related to the protocol, like an HTTP error from a web service or a database error, indicates an open port and potentially identifies the service running there. This technique is sometimes called cross-site port attack, XSPA. It lets them map out the internal network topology and find other juicy targets.
So they use the web server as their internal network scanner. Sneaky.
Very. And internal systems often have weaker security postures, assuming the perimeter firewall protects them. They might have default credentials, unpatched vulnerabilities, admin interfaces open.
We're just some. Any other major impacts?
Yeah, denial of service, DAS, is possible. The attacker could make the vulnerable web server repeatedly request huge files from an internal resource, potentially overwhelming that internal system, or even the web server itself. Imagine pointing it at file.devrandom on a Linux server.
Ouch. And you mentioned maybe even remote code execution, RCE.
Sometimes, yeah. If the SSRF allows interaction with internal services that themselves have vulnerabilities exploitable via HTTP requests, like certain APIs, backend admin panels, or even database interfaces if they speak HTTP somehow. Or if the URL parser itself has flaws, like handling file or gopher protocols, it could potentially lead to RCE on the server or other internal systems. It depends heavily on the specifics.
Okay, so SSRF is powerful. You mentioned different targets, like the server itself or the backend.
Right. We can categorize SSRF based on the target. SSRF targeting the server itself is common. The attacker provides a loopback address, 127 and SA1 .1 or localhost, or variations like .1 for IPv6.
Why would they attack the server itself?
Often servers run administrative services or monitoring tools that are only bound to the loopback interface for security. They're not exposed externally. But if the web application on that same server has an SSRF flaw, the adder can use it to make the server talk to itself via 127.0.1 and access those protected admin panels or APIs.
Ah, bypassing the network binding protection.
Exactly. Then there's SSRS targeting the backend. This is using the SSRF to reach other machines on the internal network, those private IP ranges like 10.x.x.x.x.172.16.x.x. This is where they go after databases, internal APIs, file shares, other web servers, not exposed externally.
And you mentioned blind SSRF earlier. That's when you don't get data back directly.
Right. The vulnerable function might execute the request, but not return the response content to the attacker. Exploitation becomes harder, relying on those side channels we talked about. Timing analysis for port scanning, XSPA, triggering DNS lookups to an external server the attacker controls, using something like Burp Collaborator to confirm the connection happened, or maybe causing a visible side effect like a DOS.
The sources mentioned blind SSRF via the referer header. How would that work?
That's an interesting edge case. Imagine a server has some internal analytics component that, maybe overnight, processes access logs and tries to fetch the referer URLs found in those logs to get metadata or screenshots. If an attacker can get a log entry recorded with a malicious internal URL, like http://169.254.169.254, in the referer field of a request they send,
Then the back-end analytics process might blindly make that SSRF request later.
potentially, yes. It's an indirect, blind vector, but shows how SSRF can lurk in unexpected places.
Okay. Now, defending against this, the sources seem pretty clear that just blocking known private IPs like a blacklist is a bad strategy.
Yeah.
Why?
Because attackers have countless ways to bypass simple blacklists. The core problem is that there are many, many ways to represent the same IP address, and URL parsers in different parts of the stack, application code, libraries, operating system, might interpret them differently.
Like what? How can you write 127 by 0.0.1 differently?
Tons of ways. One, alternative IP formats. Instead of 127 by 0.0.1, you can use its full 32-bit integer representation, 2130070000001. Many system network libraries resolve these correctly, but a simple string blacklist looking for 127 by 0.0.1 will miss them.
Wow, okay. I didn't know you could do that.
Yep. 2. DNS resolution. An attacker can register a domain name, say localhost.attacker.com, or use a dynamic DNS service and simply point its DNS record to 127 by 0.0.1 or any internal IP they want to target, like 10 to 0.25. If the application's blacklist only checks the host name provided by the user and doesn't check where it resolves to, it gets bypassed. The application sees localhost.attacker.com, thinks that's not a private IP string, allows it, makes the DNS lookup, and connects to 127.0.1.
So the check happens too early before the name is resolved.
Exactly. 3. URL encoding obfuscation. Attackers can use standard URL encoding, like 31% and 32%, 37% parent percent, and 33%, 30%, 30% encryption, 30%, 30% and point server to window, or more obscure encoding tricks, sometimes mixed case, to bypass naive string matching filters.
Okay, yeah, blacklisting sounds doomed. What's the alternative? Whitelisting.
Whitelisting is much stronger. Instead of trying to list all the bad things, which is impossible, you define a strict list of only the domains, IPs, and protocols that the application is supposed to connect to for its legitimate functions. Anything else is blocked by default.
But even whitelists can be bypassed sometimes. You mentioned open redirection.
Yes, this is a more advanced bypass. Let's say your application needs to fetch resources from trusted-cdn.com. So trusted-cdn.com is on your whitelist. However, trusted-cdn.com itself happens to have an open redirection vulnerability. This means there's a URL on trusted-cdn.com, like https.trusted-cdn.com, redirect.url, some other URL that'll just redirect the browser or server to whatever URL is provided in the parameter. So the attacker crafts an SSRF payload targeting your server. But instead of putting the internal IP directly, which the whitelist would block, they put the whitelisted URL, https.trusted-cdn.com, redirect.url, http:169.254.169.254.
Ah, your server sees trusted-cdn.com, checks the whitelist, says, yep, that's allowed, and makes the request.
The request hits trusted-cdn.com, which then obediently sends back an HTTP redirect, like a 301 or 302, telling the client, go here instead,
Yeah.
http:169.254.169.254.
And does the web server making the original SSRF request follow that redirect?
Often, yes. Many HTTP client libraries follow redirects by default. So your server ends up connecting to the forbidden internal IP, even though the initial URL passed the whitelist check.
That's a chained exploit. Okay, this brings us straight to the Capital One breach in 2019. It sounds like a perfect storm of SSRF and cloud issues.
It really was the poster child for modern SSRF risks. The attacker found an SSRF vulnerability in a misconfigured web application firewall, WAF, that Capital One was running in AWS.
So the wave itself was vulnerable.
The underlying infrastructure or configuration allowed the SSRF. The attacker used this vulnerability to force the WAF instance to make a request to the internal AWS instance metadata service endpoint, 169.254.169.254.
Going after those IAM credentials we talked about.
Exactly. And here's the critical failure. The IAM role assigned to that WAF instance had way too many permissions. It wasn't following the principle of least privilege strictly enough. Specifically, it had permissions to list all the S3 storage buckets in the account and read data from those buckets.
So when the SSRF hit the metadata service?
The metadata service returned the temporary credentials for this overprivileged WAF role. The attacker grabbed those credentials. Now, acting as a WAF, they could use the AWS API to list all the S3 buckets and then start downloading the data over 100 million customer records.
Wow. So it wasn't just the SSRF flaw. It was SSRF plus WAF misconfiguration plus excessive IAM permissions plus lack of detection.
That's the trifecta. Any one of those being fixed might have lessened the blow or stopped it entirely. If the WAF wasn't misconfigured, no SSRF. If the IAM role had minimal permissions, maybe just enough to write logs, not read S3, the stolen credentials would have been useless. If they had better monitoring for unusual activity like mass S3 downloads or metadata service access, they might have caught it sooner.
It's a huge lesson in layered security and cloud configuration hygiene. You mentioned cloud providers are trying to fix the metadata service risk, IMDS v2.
Yes, that's a significant improvement. The original instance metadata service, IMDS v1, was vulnerable because you could fetch credentials with a single, simple GT request, perfect for SSRF exploitation.
Okay.
IMDS v2, the newer version, requires a session-oriented approach. First, the instance has to make a PUT request to get a short-lived secret session token. Then it has to include that token in a special header in the subsequent GT request to actually retrieve the metadata or credentials.
How does that stop SSRF?
Basic SSRF payloads using standard GISHI requests, like in an MG tag or a simple URL fetch, can't perform that initial PUT request to get the token. And even if they could somehow trigger the PUT, they wouldn't easily get the token back to use in the second GISHI request, especially in blind SSRF scenarios. It makes exploiting the metadata service via SSRF much, much harder.
So rule 1 for cloud security, enforce IMDS v2 and disable IMDS v1 wherever possible.
Absolutely crucial mitigation for SSRF in the cloud.
Okay, we've gone deep on XSS, CSRF, and SSRF. Let's try to tie it all together now, focusing back on that idea of broken trust.
Right, so quick recap: XSS, cross-site scripting, targets the user, breaks the user's trust in the website's content by injecting malicious client-side script. Goal: execute code in the victim's browser. CSRF, cross-site request forgery, targets the website, breaks the website's trust in the user's browser session by forging unintended requests. Goal: trick the server into performing actions the user didn't authorize using their existing session. SSRF, server-side request forgery, targets the server and its environment, breaks the implicit trust between the server and its internal network, or itself, by forcing the server to make malicious requests. Goal: access internal resources, scan networks, steal credentials from the server environment.
And mapping that again to MRA, ATT, and CK, we see how they fit into an attacker's plan. XSS is often that initial access T1189.
Yeah, or maybe used later for persistence or privilege escalation if they can inject script into an admin's view.
CSRF comes after login, enabling execution like T1530 or privilege escalation T1134 by hijacking the session's power.
Right, using the existing authenticated context.
And SSRF is often used for credential access, like hitting IMDS, discovery, internal scanning, or as a pivot point via exploit public-facing application TILA-190 to gain deeper internal access.
Exactly. They're tools in the attacker's toolkit, often used in combination. Defending against them requires that holistic, perfect injection resistance mindset we talked about.
So let's summarize those key layered defenses for each one again. If you remember nothing else, what are the absolute must-dos?
Okay, high level. Always remember the mantra. Validate every input, escape or encode every output, sanitize user HTML. Then specifically, for XSS, context-aware output encoding is paramount everywhere. For XSS, implement a strict content security policy, CSP header. For XSS, use secure frameworks and understand their escaping mechanisms. Don't bypass them carelessly. For XSS, use HTML sanitization libraries for any rich text input.
Got it. For CSRF.
For CSRF, use anti-CSRF tokens, synchronizer or double submit. This is non-negotiable for state-changing actions. Set the same site cookie attribute to strict or lax, prefer strict. Never allow state changes via GET requests. Use post-put-delete. Consider adding MFA for highly critical actions like password changes, large fund transfers, as an extra layer beyond the session token. Maybe add origin referer header checks.
Okay. And finally, for SSRF.
For SSRF, implement strict URL whitelisting for any server-initiated requests based on user input. Block everything else by default. Blacklisting is basically useless. Perform rigorous network segmentation. Use firewall rules to prevent the web server from connecting to internal resources it doesn't absolutely need to talk to. Especially lock access to cloud metadata endpoints unless required. And use IMDS v2. Validate and sanitize the entire URL, not just the host part. Be careful about protocols allowed. HTTPS only, no file.or gopher. Validate and sanitize the entire URL, not just the host part. Be careful about protocols allowed. HTTPS only, no file. Consider disabling redirects if your HTTP client allows it, or validate to the post-redirect location.
It feels like these are all known problems with known solutions. Why are we still seeing them so often in breaches and vulnerability reports? What's the disconnect?
It's a combination of things, I think. One is just the sheer complexity of modern applications, microservices, APIs, complex JavaScript front ends, third-party integrations. There are just so many more places for these flaws to creep in. Developers are under pressure to ship fast, and maybe security training hasn't kept pace, or they make assumptions about framework protections.
Like the framework handling everything, which we know isn't always true.
Right. And specifically for XSS, handling user-generated HTML safely is hard. It's easy to get sanitization wrong. For CSRF, legacy systems often just relied on cookies, and refactoring them to add tokens can be a big job. Or in complex systems, maybe session management gets tricky and developers take shortcuts.
And SSRF seems almost amplified by the cloud.
Definitely. The implicit trust in cloud environments is a huge factor. The ease with which a server instance can access powerful metadata services via SSRF turned a standard web flaw into a potential company killer, like we saw with Capital One. The architecture itself, while convenient, created a high-value target for SSRF. Plus, properly configuring network segmentation and IAM roles in the cloud requires expertise that not all teams have.
So it's a mix of complexity, legacy issues, lack of training or awareness sometimes, and the specific challenges introduced by modern architectures like cloud.
Pretty much. And maybe sometimes the perceived impact is underestimated until it's too late.
It really drives home that security isn't about one magic bullet. It's about consistently questioning and verifying trust at every single boundary browser to server, server to database, server to cloud API, server back to itself.
Well said. Challenge that trust constantly. Assume nothing is safe by default.
So what does this all mean for you, the listener, as you think about your own applications or security practices?
I think one key takeaway is that while we dove deep into the technical details of XSS, CSRF, and SSRF, don't forget the human element that often enables them. Especially for reflected XSS and CSRF, the attack often starts with social engineering.
The phishing email, the dodgy link?
Exactly. If the user never clicks the link, the exploit chain breaks before it even starts. So user awareness training, phishing protection, email filtering, those remain critical frontline defenses that complement the technical application security measures.
Good point. And looking ahead, any final provocative thought for us to chew on?
Well, thinking particularly about SSRF and the bypass techniques, we discussed the IP encoding tricks, the DNS resolution games, the open redirects. It highlights a fundamental challenge in security design. Given how incredibly difficult it is to reliably identify and block all possible malicious destinations, a blacklist approach. The question becomes, how confident can any organization really be in a security posture that relies heavily on blacklisting versus one that commits fully to a strict default deny whitelisting approach for all outbound connections initiated by servers? Moving decisively from block the known bad to only allow the explicitly known good seems like the only truly resilient path forward for mitigating sophisticated SSRF. But it requires significant discipline in design and operations. Is your organization truly ready for that?
That's a heavy question to end on. From blacklist fragility to whitelist discipline, definitely something to think about.